Hey, problem 3. Here we have something slightly more interesting. In the end, we want to prove this, the formula for summing up the third power of integers. It can be proved directly by induction, but maybe that's not fun, or the pattern of this formula might be not so obvious to be spotted, so we use this way above. So let's break it down and do it questions by questions. So the first question is easy. It is just ask you to do the summing up of an arithmetic sequence, and that was easy. We use the most classic way of proving it. We make a copy of the sequence and reverse it. Yeah, with success, we make a copy and reverse, and for each one, we pair them. And they should be equal n1 plus n2 each. So we add them together. We have 2s, which is the twice of the sum we want, equals, okay, they are n2 minus n1 plus 1 pairs, so it is plus 1 plus 1. So they are n2 minus n1 plus 1 pairs of n1 plus n2. Therefore, the sum should be exactly this. Quite trivial, right? Yeah, let's go. And let's look at the second part, the real part. So there is interesting thing that this is square number, this is square number, this is square number. If this is n, yeah, and on the right side, they are all cube number. Cube. Yeah, they're all cube number. And if we say this is a cube, this will be n minus cube. So we are thinking about why this thing might help us prove the summing up of the third power of integers. So it would be obvious that if we add these things up, we add them up, and at the right side, we get what we want, but with one n cube missing. So exactly that twice what we want, but n cube missing. On the left side, we got something like a sum of an arithmetic sequence, which can be solved by our previous findings. So right now the thing is we have to prove this. So we write this general law and we try to prove this. And maybe we can prove the final formula. So what we spot here is so they are all square number. If we say this is n cube, this will be n minus cube actually. Because 64 is 4 cube, right? And this is 4 squared, so it will be n squared. This will be n minus squared, right? So this is actually n minus 1 squared plus 1. Yeah, let's go. So what we want to prove here is actually we want to prove n minus 1 squared plus 1 plus n minus 1 squared plus 2 plus 2n squared equal n minus 1 cube plus n cube. This is what we want to prove. And this has actually nothing to do with induction. The left one, it is just a arithmetic sum. We can use what we get above, how to sum them up. It is basically 1 over 2 times, so n squared minus n minus 1 squared plus 1 and minus 1. So we get 1 cancelled out, no constant here. And we have n minus 1 squared plus 1 plus n squared. This is the left-hand side. Our mission is to prove it is equivalent to the right-hand side. So we can prove this general law. Actually, we can compare the degree for now. It's important. Its degree is 2. Its degree is 2. So maybe there is a problem. We know that here actually we can cancel out the degree of 2. But yeah, let's do some calculations actually. It's 1 over 2 n squared minus n squared plus 2n is 1. So this is actually very basic. I think everyone should be able to do this quickly. Yeah, we cancel out the quadratic thing. What we have right now is this. And this can be factorized, so we get this. I don't know if it looks familiar to you, but there is a very useful result I think everyone should remember. The a cubed plus b cubed equal a plus b times a squared minus ab plus b squared. So applying this, we don't have to expand this or expand this. We don't have to expand them. So n minus 1 cube plus n cube equal, so applying the formula is m plus n minus 1, which is 2n minus 1, n squared minus n times n minus 1 plus, sorry, I reversed the positions, but not serious. Yep. Fun, n squared plus n. And surprisingly, this is it. But we do it with another direction actually. So this will be exactly n minus 1 squared plus n squared. And this is what we have right hand side. So we prove them. And now we are adding them up. Adding them up. On the left hand side we get 1 plus 2. So right, 1 plus 2 plus 3 plus 4 be plus until n squared plus until n squared. Right hand side we have 0 plus n1 cube plus 1 cube plus 2 cube. We plus to the n cube. And this is actually 1 cube plus 2 cube plus n cube. But there's actually only 1 n cube. So we have to minus 1 n cube. For the left hand side, but I mean here we want this. So clearly we do, but only just keep it in mind. We are not that hurry. So we first do the left hand side. We do the sum. This is easy. This is it. And this is the sum we want minus n. So that's equal. And we plus 2 squared. Actually, we can factorize by a n squared. 1 plus n squared plus 2n actually. And you can complete in the squared, m plus 1 squared. So yes, I think we get it. Yeah, so now we finally reached the final result. It is n squared times n plus 1 squared over 4. It's our final result. Yes. That's the end of my solution to problem 3. Hope you enjoy it. So what we have done these days are just quite easy. So it's just some pre-kindergarten questions, but I mean we will have something more interesting later.